In this video, we explain the design of the binary coded decimal Ripple counter. BCD Ripple Counter is a counter that follows a sequence of 10 states and returns to 0 after the count of 9. Therefore, it counts as follows from 000 to 0001, 00102, and then 3 in binary, 4 in binary, 5 in binary, 6, 7, 8, 9 in binary, and when it reaches 9, the counter must reset itself, which means it will go back to 0. So this is the state diagram, and in order to design the counter, we believe the best way is to watch out the way the bits change as we count. Now, we have to keep one thing in mind. When we count from 0000 to 0001 to 0010, etc. Now, each time when one bit changes from 1 to 0, the bit in the next position will change, either from 0 to 1 or 1 to 0. So keep this rule in mind because we will need it. Now, the best way to design the counter is, again, as we mentioned, to see how does the different bits change. Now, if we call the 4 bits of the counter Q1 the least significant, and Q2 the next one, and Q4 and Q8, where 8, 4, 2, and 1 are the weights of the bits in the binary coded decimal as we have studied earlier. Then, if we look at the Q1, it was 0, and then 1, 0, 1, 0, 1, etc. We can conclude that Q1 changes state after each clock pulse or after each count pulse. So that is very easy. Now let's look at the Q2. Q2, which is this bit here, it was 0, and then it is 1 here, and then 1 here, 0 here, and so on. So we find that a Q1 complements every time a Q1 goes from 1 to 0, as we just explained on the previous slide, but this remains true as long as Q8 is equal to 0, which is in the first 8 states. And then when Q8 becomes 1, which is this state and this state, Q2 remains at 0, which means this is 0 and it stays 0. This rule is very important, actually, to understand in order to be able to build the hardware, because the hardware will depend upon how do the different bits change. Now, going to Q4, Q4 is easy because it complements every time Q2 goes from 1 to 0, which is consistent to the rule that we described earlier. Don't forget that. This is a Q2 and this is a Q4. So when a Q2 goes from 1 to 0, a Q4 will complement. And this is the normal way of counting. Finally, a Q8 remains at 0 in the first 8 counts from 0000 to 0111. Q2 remains at 0 as long as Q2 or Q4 is 0. If we look at these states, the first 8 states, this is Q2 and Q4 are zeros here. And here Q2 is 1, Q4 is 0. Here Q2 is 1, Q4 is 0. Here the reverse, Q2 is 0, Q4 is 1 for these two. And then when both Q2 and Q4 are 1s, what will happen is that Q8 will be cleared, which means now going from this state here, this is 1, 1, Q8 is 1 here, and the Q8 is clear on the next transition of Q1, which means when Q1 goes from 1 to 0, we clear Q8 so that from the state 9, we go to state 0. Now, these rules, as a matter of fact, will enable us to design the hardware. Design will depend upon what type of a flip-flops do we choose. If we choose the JK flip-flops, then the counter will be designed as follows. The first flip-flop will be Q1 here, and then Q2, and Q4, and Q8. Each flip-flop will have JK inputs, and according to the rules, Q1 must change state after each clock pulse or after each count pulse. So we connect the count pulse to the first flip-flop. So each count pulse, when the count pulse goes from 1 to 0, so this is the count pulse like this here. So at this edge here, and this edge, and this edge, and this edge, each time it goes from 1 to 0, we want the Q1 to change, which means it will go 0, 1, 0, 1, 0, 1. This can only be done if J is 1 and K is 1. So we connect J and K of the first flip-flop to logic 1, as we can see here. So we are done with this. Now let's come to Q2. Q2, the rule that we have just derived, it complements every time Q1 goes from 1 to 0, as long as Q8 is equal to 0. And if we connect Q8 prime, so this is Q8 prime, when Q8 is 0, this here will be 1, which means this will be 1, as long as Q8 is 0. So this is this part of the rule here. And K is 1, which means Q2 will complement when Q1 changes from 1 to 0. So Q1 is the clock of the Q2 here. However, when Q8 becomes 1, so when this becomes 1 here, this will be 0, and this will be 0, and this flip-flop will have J equal to 0 and K equals to 1, which means when Q8 becomes 1, Q2 remains at 0, which means this will be reset at this change here. So that's when K is 1 and J is 0, it is reset. And then we go to Q4. We said complements every time Q2 goes from 1 to 0. So all what we do is to connect the Q2 with the clock of the Q4, and we make J and K of this flip-flop equal to 1. That's easy. Finally, the rule for Q8, we see the Q8 remains at 0 as long as Q2 or Q4 is 0. Therefore, what we do, we connect a Q4, that's a Q4, and that's a Q2 to an AND gate. So when either is 0, this will be 0. And when both are ones, this will be 1. When either is 0, this is 0, K is 1, and J is 0, which means Q8 will remain at 0. It will be reset. On the other hand, when both are ones, this will be 1, and when this changes, this flip-flop will complement, which means it will go to 1. So this is really the design of the counter based on the rules that we derived. And the best way for you to check that it works correctly, you can put the counter at 0, 0, 0, 0, and you will see that at the count pulses, as they go, it will move to 0, 0, 0, 1, and then it will move to 2, and 3, and 4, until 9, and it will go back to 0. So you can easily verify the counter by analyzing. Finally, what we have studied is one digit of the counter. So this is what we studied. This is the logic diagram that we have just seen, and one digit is really nothing. Usually we need several digits of a counter. So if we look at the car odometer, it has 6 digits as an example. So it can count until 999999999. So it has 6 digits. If we look at a 3-digit counter, we call it a 3-decade decimal counter. We need 3 of the counters that we have just seen. So what do? We connect the count pulse to the least significant digit, and then a Q8, when it makes transition from 1 to 0, we connect it as input to the next digit. Same thing here, Q8 will be connected to the input of the next digit. So the way it works, this counter will count 0, and then 1, until 9. So after 9, it will go back to 0. When it goes back to 0, Q8 will move from 1 to 0, which means it will make this counter count. So we start with the counter 0, 0, 0, and when it reaches 9, this will be 0, and this will be 1. So it counts from 9 to 10, of course, because that's the 0, and that's the 110. Again, this will count 1, 2, 3, 4, 5 until 9, so it counts to 19. When it counts to 20, this will be 0, and this will be 2, and so on. Will go 20, 21, 22, until 29, and then this will be 0, this will be 3, and it will keep counting until this is 9, and this is 9, and this is 0, which is 99. Next time, this count will be 0. This will change it from 1 to 0. It will make this one count. This will be 0. This will change it from 1 to 0, and this will be 100. So we count 100, 101, 102, and so on until we reach 999. So we start by building one-digit BCD counter, and from this digit, we can easily have multiple decade counter. We can put as many digits as we want.